So today we are going to talk about the deep learning. So deep learning is one of the key area of AI, which is artificial intelligence. So before get started, right, we'll just quickly introduce ourselves. So my name is Ashok Srinivas. I'm a machine learning scientist at PayPal, and I have 8 years of experience. Prior to PayPal, I used to work for DBS as a applied data scientist. And I'm also currently pursuing my master's from IIT Jodhpur. It's a distance degree which I'm pursuing right now. Maybe maybe I have one more semester. I have my thesis as well. And now I let Bhartendu to speak about himself. BK, over to you.
Hi everyone, I'm Bhartendu Thakur. I'm machine learning scientist in the same team as Ashok. We are working for Global Analytics and Data Science Org. And prior to PayPal, I have worked with Mercedes-Benz as research engineer and innovation incubator. As an advanced scholar, I have completed my master's in machine learning and computing from IST. It's part of ISRO. So I'm happy to speak to all of you. I am unable to see you people, but I'm hopeful this session we are able to contribute something to your life. Over to you, Ashok.
Thanks, BK. Thank you very much for introducing yourself. So now coming to the agenda, so we will initially quickly see what exactly deep learning is all about, and we will see what exactly the neuron and multi-layer neural network is, and we'll also see the structure of it, and the working applications of deep learning, and also some of the use cases which we are using in PayPal using deep learning. And post that, I'll let Bhartendu talk about computer vision. He will walk you through the computer vision concepts like I mentioned before. And then I'll talk about natural language processing, in which we will see different methods of encoding, vectorization, and transformers. GPT, most of you might have some understanding about GPT, right? There is something called ChatGPT. So how they have worked. I'll not talk more about ChatGPT, but I'll talk about the core concept of GPT. Clear so far? Cool. So first of all, we will see what exactly this AI is and what is ML and what is DL. So DL is deep learning, ML is machine learning. So AI is a kind of field in computer science which actually tries to build the machines which mimics the human intelligence, right? So when I say human intelligence, the machine which this AI builds should be able to take the own decisions based on the data we pass. And machine learning is one of the sub part of this AI, and along with deep learning. And this machine learning actually uses different statistical models. So these models actually extract the patterns in the data, and that patterns we will use to make a certain decision, or maybe we can pass that information for our downstream tasks. And coming to deep learning, unlike machine learning, it will not use any predefined algorithm. It uses neural nets. So what this neural nets does, it tries to learn based on the number of iterations we pass to it. Let's say when I pass a data to the deep neural network, initially it may not perform well, maybe initially it may not understand what we are passing, but by training it again and again and again, when I say again and again and again, it's all about epochs. There is a concept called epoch. If you're not familiar, maybe you don't need to worry about that. So we will train the model well. Once the model is converged, then the model is able to take a better decisions, right? So the only difference between ML and DL is, ML is machine learning, like I said. Machine learning and deep learning is, in deep learning we use neural nets, which actually is a which resembles a neuron in our brain. So you guys know neuron in our brain, right? And the functions of it, isn't it? So what exactly our neuron does? It passes the signals and make us to take a better decisions based on the information we have, right? In a similar way, even the neural nets also tries to pass the information to the other neurons, and also it will help that model to take a better decisions. We will talk more about this neuron in the next slide, and also we will see how this neural network works and what is the connection between the neuron we have and the neural nets that we will be training, right? Any questions here before I move to the next slide? Great. So coming to multi-layer neural network and the structure of it, as you can see here, the right side of the slide, that is the structure of neural network. So it contains an input layer and an output layer at the end, and in between we can have multiple hidden layers. So when I say input layer, we pass the data or the information. Let's say you want to classify an image. You have a set of 200 images in which we have a mixture of dogs and cats. Now the task of yours is to classify the images properly. If you do manually, it is a pure manual effort, but if in case you want to use machine learning and AI, then you have to train a model. So to train a model, what we need to do, we need to pass some information to the model so that the model can understand the patterns, right? So let's assume that you have a newly born baby. So if you give this image to newly born baby, will baby able to classify it properly? No, right? Because baby doesn't know anything about the images that you are passing to it, isn't it? So baby needs some time to understand the real world, and it will get the exposure, it will learn, and then it will be able to classify. So the neural network which I am talking about right now is also a kind of baby to us. So initially it will have zero learnings. So we need to pass the data to the neural network, and we should make it understand what exactly our task is all about. So when you pass the data to it, it will try to understand, and also it needs some prior information as well. It's not like you pass it and it will learn. You need to give some prior information as well, like what image comes under dog and what image comes under class. Based on that information, it will train and learn, and it tries to take a better decisions in production or when you really want to use it. Clear? So now input and output layers actually will help us understand that. So input layer actually takes the data into consideration, and output layer gives us the final output. Maybe it can be a classification. Are you guys familiar with classification? Yeah. So when I talk about the classification, you will be classifying whether it's a dog or cat, isn't it? And coming to the hidden layer, so hidden layer is where the actual neurons plays a major role. So before going to that, I'll talk about the neuron first. So as you can see here on top, that is the structure of the brain neuron, where the dendroids capture the signals from the other neurons, and the tail of this particular neuron will pass the signals to the other neuron, right? So this consumes the signals and pass the signals to the other neuron, and it is a kind of passing the signals to each and every neuron. So whatever the information one neuron knows, the other neuron also will be able to understand it, because the signals will be passed accordingly. So it will interlink with each other in our brain. Similarly, our neural network also will be was structured in a similar manner. So we will be having multiple neurons, and each and every neuron will be connected with the other neuron, so that the information can be passed to the other neurons. As you can see here, the arrow marks denotes that. So the input neuron, if you see the first neuron, so this is the neuron, and this neuron is connected to the other neuron in the hidden layer. So likewise, the information will be moved forward. Now let's see what exactly the neuron does. And also, as you can see here in diagram, the neuron of deep neural network and the neuron of brain are similar in terms of structure, and also it is similar in terms of functioning as well. So the neuron accepts the inputs in a generic terms. It can be signals, it can be treated as a signals, but when you come to the machine learning domain, we can say it as a kind of data. So it accepts the data, and we have something called summing junction. So what it does, it captures all the information and it collates and passes to some other layer, which is activation function, which actually normalizes and pass the output. So the combination of these neurons is nothing but the neural network. So this input information will be passed to the other hidden layers, and these hidden layers tries to understand what kind of data we are passing with the help of weights. So I'll talk about what exactly these weights are, but I'll just give a brief introduction about that, but I'll not go too deep into the math, right? So we will give certain weightage to each and every data point we have. Let's assume that I have given you an image of a dog. Okay. Now, if I ask you to look at it and say what is that animal is, what you will do? So you will just look at it and you will say it as dog, right? So what is the reason behind that? So what exactly you're doing over there? So when you look at an image, what you observe there, how you are classifying whether it's an image of a dog or a cat. Can anybody say? Yeah, please. Features, right? Nose, ears, and eyes. Puppy eyes. We have this puppy eyes for dogs, right? So we will not look at each and every pixel of an image manually to classify it whether it's a dog or image, dog or cat, isn't it? So what we do visually when you look at it, we will observe only certain points, maybe ears, maybe eyes, maybe nose, maybe tail, maybe the size of an animal or the shape of an animal. So these are some of the features that we will look at it and classify. Similarly, when you pass a huge set of images to the deep learning or a neural network, it will give certain weightage to the different features it observes, right? So these weights actually plays a major role in to finding out the right features. Clear so far? Yeah. So now, in that way, the information will be moved forward till the output layer, and the output will give us a probability of each and every class. Let's say if we have two classes, class dog and class cat, if you have a probability of 0.2 for class dog and a probability of 0.8 for class cat, then which one you pick? Which one is the final decision here? Since the probability is higher for cat, so we will say the final decision is cat, right? So that is what the neural network tries to inform us. It will give some score for each and every class, and we will see which class has a higher probability, and we will take that as our final decision. And now the neural network learned something in the feed forward, and now it has to see or it has to validate whether the learnings are valid or not, right? So here there is a beautiful concept called validation, right? So when a neural network actually tries to predict something, we need to understand whether that is right or wrong, whether that is true or false, isn't it? So for that, we need to come up with a function called cost function. With that, we will observe what is the loss in that. Let's assume that my neural network predicted it as dog, but the actual class is cat. So there is an error. So there is an error in understanding the image, isn't it? So what you need to do? You have to adjust your weights, because the weights that we have given to different features are not actually making sense, isn't it? So now what we have to do, we have to adjust our weights. So for that, we have to backpropagate. So there is a concept called backpropagation, which actually adjusts the weights according to the error we have got. Clear? Right? I guess there are few new terms for you guys like backpropagation and feed forward and weights. But if in case you have any other question on these, right, just let me know. I'll try to explain it more. Please. Actually, I couldn't hear you. Can you be a little more? Can somebody tell me like what he's saying? Why? So why it will learn? Because of the algo we have inside it, right? So there is this neuron, isn't it? So basically, the numerical representation of the data inside the deep learning or the neural net, we are considering it as a learning, isn't it? So why it is learning is not a right way of looking at it. How it is learning is what you should look at, if you ask me, because the reason that we are using neural network is to make it learn, isn't it? The internal math that we have under the deep learning is to make it learn. So our sole purpose is to make it learn. So the existence of this neural network is to make it learn, isn't it? So we should understand how it will learn than why it learn. Clear?
Sir,
Yeah.
can we train a neural network using just single neuron? We can't do that, right?
We can't do that. We can't. Definitely. It's just compare your brain with a neural network. With a single neuron, with a single brain neuron, will you be able to do anything?
No, sir.
No. Same applies here as well. With a single neuron, you can't do anything. So we need a huge bunch of neurons to learn something good, isn't it? So when you pass the data is not very small or very linear, right? The data is not very easy to understand. If it is very easy to understand, then we don't need a deep learning model.
We need machine learning models for that.
Exactly. Not even machine learning model. We can just go for a simple rule-based model, like if-else conditions will do.
Okay.
Right. So when you have a huge set of data, so it is difficult for you to explore the data and the patterns inside it. For that, we need a mechanism which can actually learn with the help of some statistical algorithms, right? So neural networks and machine learning will help us do that.
Okay, sir.
So if you take an image, a single image will have a lot of information. If you take an image of a dog, in that image itself, you will be having a lot of information like eyes, nose, ears, tail, body shape, fur, and everything, right? So you can't look at all the dimensions of the image, or you can't look at all the dimensions of the data, isn't it? So we need certain mechanism which actually help us do that.
Okay.
Clear?
Sir, are you going to explain backpropagation also?
Not in this session, because we have a lot more things to cover. We are not actually we are not actually touching the math here. We will just introduce few algos and few technologies that are out there, so that you can kickstart your journey in data science or machine learning.
Actually, I don't understand the backpropagation thing only in the neural network.
Let's do one thing. Maybe we can connect offline. I can help you understand.
Yeah, that
Right?
will be great.
Because we only have 2 hours, so we want to cover everything that we
No
have.
problem, sir.
So, sorry to cut you down over there,
No
but
problem.
we will connect offline and I'll make you understand, and
Okay,
I'll
sir.
also give some real-time examples as well.
Okay, thank you.
Awesome. With that, I'll be moving to the next slide, which is applications of deep learning. I guess most of you, yeah, please. Activation functions, right? So basically activation, bias, right? So first I'll talk about, yeah, please. Sorry? Kernelization. Frankly speaking, this is the first time I'm hearing this kernelization. BK, have you ever heard about this kernelization?
Meaning
Kernel function. Okay, so is it related to SVM? Okay. Okay, that's a dimensionality reduction, isn't it? PCA generally used for that. So you want to understand what is the difference between them, right? Okay, I'll just quickly give a brief about it. I'll not dig deep because, like I mentioned, because of the time, we have to run quickly. I'll just give a quick introduction about that. So kernel, which you mentioned, that comes in SVM, okay, that converts the low dimensional data to the higher dimensional data so that it can be easily separable, right? When you have a non-linear data, let's say, I guess you might have seen this example of circular data, right? And also a cluster of 2 different data points where you can separate the two clusters with a single line, isn't it? So now coming to that concept, so kernel method actually will be used to transform the data. It will transform the non-linear data into linear data, in particular low dimensional information to higher dimensional information, where we can easily separate the data with a best fitting line. That is with respect to kernel in terms of support vector machines. And coming to the PCA, so PCA is generally used to reduce the dimensions, okay? When you have a huge number of features, let's say 1,000 features you have, and it is difficult for you to pass those 1,000 features to a model and train it. Sometimes you may indirectly pass noise to the model as well, and the model will underfit as well. So in that cases, PCA will be used so that, the ultimate intuition of PCA here is to reduce the dimensions, and it will not drop the data, but it will create the dimensions in such a way from a different angle of information. If you look at the data in a 360 degrees, maybe it will convert it into 180 degrees and reduce the number of dimensions. Something similar. Like I'm not actually giving a mathematical explanation, I'm giving a theoretical explanation over here, because if we start talking about that, it will actually go to a huge discussion. Definitely I'll connect with you after this call, after this session. I'll make you understand what exactly that is. And coming to the activation function, so activation function is used to normalize things, right? So if you take a sigmoid, right, it ranges from 0 to 1. So whatever the value passes, that range, like you can't actually create a score when you have a higher value. So to keep the whole scores in range, we will use a sigmoid which actually ranges from 0 to 1. Let's say when I said the score probability for a class, right? So the output of a particular neuron will be always will be more than one. Like when I say always, most probably it will be more than one. If it purely depends upon the weights. If the weight is if the weight value is higher, the output of neuron will be higher. So with that, you can't actually come up with a probability, right? So you use some kind of functions. You need to pass the information as well. There is some activation function called ReLU, leaky ReLU, which actually make the information pass to the next neurons. So it is not only a normalization, it actually depends upon what you want to make. So sigmoid is majorly used at the end of the model, like when you want to create a score. But ReLU and leaky ReLU helps us to pass the information. There is a concept called vanishing gradient and the other one second, exploding gradient. Yes. So these activation functions helps us overcome such kind of issues. So like I mentioned, it's a kind of chain of concepts. So that's why I'm just giving you the brief introduction about the deep learning without touching the actual mathematical concepts, right? So since you talked about the activation, it actually connected to the exploding gradient, vanishing gradient. If I have to talk about them, then I need to talk about the gradient descent algorithm. If I have to talk about the gradient descent algorithm, then I have to talk about the challenges of deep learning, right? So it's a kind of chain reaction. If we touch one particular concept, it will end you to other concept. The chain will never end, right? So that's why our major intention was to give as much of information to you so that you can kickstart your learning as well. Because deep learning or machine learning is a very wide subject and it is also very dry too. So we want to create a path for you guys. With this explanation, did you guys got any kind of understanding on what you have asked? Awesome, clear. With that, I'll be moving to the next slide. Sorry, I'm running because we have a lot of slides to cover. Sorry about that. Yeah, coming to the deep learning applications, most of you guys know deep learnings can be used in image classification and object detection, right? So when I talk about image classification, when you have a huge images of anything, it could be animal classification, it could be anomaly detection of a particular domain, or it could be like classifying the leaf diseases, something like that. So it could be anything. When you have image and you want to classify, a deep learning will be used over here. And an important thing that I want to highlight over here is, without deep learning, image classification is nearly impossible. With machine learnings, you can't pass all the information to the normal ML models like decision trees and random forest. So deep learning is must and should in this kind of image processing or object detection. And coming to object detection, it's about detecting the object. Let's say you might have heard about this face recognition, right? In your cell phones. So when you keep your mobile in front of you, there will be a lot of other images in your background as well. But it will not capture that. It will only capture your face and it will try to understand whether it is you or someone else, right? In those applications, this object detection will help you. If you consider the whole image instead of detecting your own face, if you consider the other images as well, it will become noise to the model itself, isn't it? So it is, you don't need to process that kind of information. You just need to concentrate on what exactly you need, basically. Clear so far why we need image classification and object detection, especially object detection? Any questions? Great. And the next one is natural language processing. I guess most of you guys know about that. Twitter sentiment analysis is one of the best use case that I can say. And chatbots. Recently, ChatGPT came into picture and we could see a conversational journey over there. So in those, creating those kind of conversational chatbots, we need deep learning. And speech recognition, I guess other feature in our mobiles, when you talk, it will unlock, isn't it? How it will know that you are the person who actually spoke? It actually relies on deep learning models. It will try to recognize whether the voice that came is yours or somebody else's, right? And the other one is recommendation system. When you go to Netflix or Prime, Amazon Prime, or maybe when you go to Amazon website to buy something, we will see a lot of recommendations, isn't it? Or if you go to Myntra or a Flipkart, you could see a lot of recommendations. How they come up with those recommendations? It purely depends upon your historical data or the similar users like you, and it compares your information with the similar users like you, and it creates some kind of metrics internally and recommend some products to you guys. So there is a huge concept of metrics factorization, collaborative filtering, content-based filtering. So all these things will also come into picture. But for now, what I wanted to highlight here is even recommendation system relies on a deep neural network. So recently, most of the companies are using neural collaborative filtering. It's a combination of neural network with collaborative filtering. So these deep learnings actually plays a major role in recommendation systems as well. And the other one is fraud detection and forecasting. Fraud detection, most of you guys know as well. When there is a fraudulent transaction, then the organization or the payment gateway has to take something from their end. They should block, or maybe they should flag it to you. So such kind of behaviors needs to be captured using deep learning and forecasting. I could say weather forecasting or sales forecasting or stock forecasting. Maybe people who are into this stock domain, right? They may understand about this. They actually eagerly want to understand what could be how the patterns will be in terms of stocks, how the trends will be, whether there will be increase in trend or a decrease in trend, right? So to understand that kind of information, we need deep learning. And the generative models, you might have seen this. When you give a text, when you describe something, it will give us an image. Have you seen such kind of tools these days? Right? Recently, even Adobe also came up with something like that. When you just highlight a particular part of an image and you type something, it will create that particular image in that particular position which you selected. So it's called a generative AI. So it generates based on what kind of input you give. Let's assume that if you take a picture of this and you want some rock star to be there along with you, then you can just type it and that person will sit here in that particular image. It's a kind of information generation. Though the information is not available, it will generate. So generative models actually helps us to generate which is not existing. So such kind of models are very interesting to actually work on, but at the same time, it is too complex as well. And the other one is robotics and autonomous vehicles. Robotics, you guys know, it will automate everything. Whatever you need to do, robots will be doing that. Let's say recently I have seen a restaurant introducing the robots to serve the customers, right? So how it will learn, how it will understand, whom to serve what. So again, deep learning will play a major role over there. And autonomous vehicles, Tesla. So you don't need to drive, you will let the car decide what needs to be done. If suddenly something comes in front of you, then it will take a smart decision. It will choose what to do, whether to brake, whether to stop the car, or whether to take a turn. It will take a decision, depends upon the possibilities that it can see. And there is something else that I want to talk about, which is reinforcement learning, which I forgot to add here. Reinforcement learning is something which the deep learning learns from the existing behavior. So let's say you train now, and when the model is in production, when people are using the model, then there will be some change in behaviors. Then you have to retrain it again to capture that behaviors. But reinforcement learning, what it does, it tries to understand that behavior and adjust the model accordingly, just like human. So that is another one which, actually that is another domain which deep learning is being used over there. And coming to the applications of PayPal, these are some of the applications which we are working on right now in our company. One is recommendation engines. We are creating a product recommendation engines in PayPal. Sentiment analysis and chatbot creation, which is common across all the organizations. When you want to track the sentiment of your user and you want to enhance the experience of your users, then these two are the most common use cases under machine learning or deep learning. And reinforcement learning, which I talked about right now, it acts like a human. It takes own decisions and validate it with the real-time data. And object detection and OCR. So in PayPal, what we are doing, we are scanning the cards. I guess you might have seen that in Paytm also right now. So when you have a card, you don't have to manually enter the details of your card. You can just scan it and let the application take care. So what this application does, or what this deep learning model does, it will capture what information is there on the card, and it will auto-populate everything in the respective field. So that is where the object detection and OCR comes. In PayPal, we are actually dealing that. And the other one is a most common thing in fintech domains, which is fraud detection. So we need to understand what are the fraudulent transactions and who are fraud users. that needs to be done. So we are dealing with fraud detection and demand and CV forecasting. So can you guys hear me? There is something wrong with this mic, guys. Can you hear me now? Yeah, I guess. Okay. So demand and CV forecasting. So it's all about forecasting, and CV is about customer value. How much value this customer can bring in future is what we are going to forecast. So BK, who is the other speaker, has worked on this CV forecasting thing. And we have something else called propensity modeling. I guess most of you guys never heard about this, because this is the word actually will rotate around in IT companies more. Like, we will try to understand the propensity of an event. Let's say you are you don't have a credit card, let's assume. Now, based on your historical transactions, we will try to understand what is the probability of you taking a credit card in the next 1 month or 2 months based on your historical data. So based on such models, we run some campaigns. So you guys might have got some customer care calls and some advertisements from your banks and everything, right? So the backbone of such calls are nothing but the deep learning models. It will understand what you will be doing in the next 1 month or 2 months. Sometimes you might have heard about this as well. Like, you will be trying something out, or you might be thinking something, and suddenly somebody calls you with that information, right? That's purely a deep learning model. So there is no magic in that. So we will just try to analyze your information well and let the model decide what kind of information or what kind of advertisement that we need to show you. So it purely depends upon your behavior. So like, we won't be believing like there will be a lot of patterns that we will show to the the applications that we use. So when I worked with DBS before PayPal, so there we are capturing your location information as well. So you might have got that request as well when you are using applications. You will let the app know where you are. So such kind of information also plays a major role. So in like, propensity models actually consumes all such kind of information and gives the best offers and best deals, right? And the other one is generative AI, like I mentioned. So generative, currently PayPal is stepping into this generative AI domain, where we are coming up with a chat GPT kind of conversational bot, which can be customized according to the PayPal standards. So these are the different applications we have. Any questions so far? I mean, in applications, do you have any questions? Yeah, please. That's confidential. I can't reveal that. Yeah. So recommendation engines recommends multiple products to you, but yeah, so he asked what is the difference between recommendation engines and propensity models, because it sounds similar, but recommendation engines considers 100 to 200 different products into consideration. Accordingly, it will recommend products to you. Let's say, let's take Amazon into consideration. So Amazon creates a recommendation engine based on the products it has, right? But it has to create if in case it has to create a propensity model, what it will do? It will create a propensity model on Amazon Pay or Amazon credit cards, or maybe a deal between ICICI and Amazon Pay, or a deal between ICICI and Prime subscription, something like that. So these are the different offers. So these propensity models tries to understand whether you will be interested in that or not. So we will take different information, we will take different user informations, and we will see who will be similar to your transactions or who will be similar to your behavior. And we will understand what his behavior, and we will see what your behavior is. Based on that, we will give certain deals to you, which you can't say no to it. Clear? So, a recommendation model talks about the products. Propensity model talks about the campaigns or deals. Deals. Let me give you this example. You have a bank account. In which bank you have? SBI. So now, what products that it gives? Let's say maybe loan. Loan service is one thing, and maybe transactions, send money kind of thing, and credit card, debit card, right? So these are services that it will recommend to you. If you build a recommendation engine, these are the different services that you will recommend to the user. But coming to propensity, So what this propensity model tries to understand, let me give you an example. Increase your limit of your credit card, okay? Extend the limit of your debit card. Opt for or use this particular code for your next Goa trip or something. So these are different deals that bank provides by looking at your historical data. So the propensity models helps us to run the campaigns and the advertisements. So you only look at advertisements, or you can say adoptions. You know, you have something, but you are not doing anything. So it will run some advertisements. You will get some customer care calls saying that you are eligible for 5 lakh instant loan. What is that? It's an advertisement, right? So it will understand your limits of your bank account, and it will see how much your transactions are, how many transactions you are doing per month, and what is the maximum limit, minimum limit, and where you are working, in which regions you are in, what is your profession. So based on that, it will understand whether you are whether you will show interest to take that loan or not. Clear? So propensity model talks more about the campaigns and advertisements. Recommendation talks more about the products or the services that the bank or the company provides to you. Clear? I hope I cleared your question. Yeah, thank you. There is a small gray area between these two, which we need to understand basically. Exactly. And the propensity model tries to capture, or it's a kind of predictive model basically. A recommendation model is not a predictive model. It's a kind of it's totally a different domain. So it will not predict. It will suggest. Let's say if I recommend something to you, I can't surely say that you will associate with that. I can't surely say that you will interact with that. Let's say you take a Netflix. You will have 30 to 40 different movies on your homepage. Will you be interacting with that? No. Sometimes no. You can't interact with all 30 movies, right? Maybe one or two, hardly 4 or 5 in month, isn't it? So that's the recommendation engine. So there is a possibility of you interacting with it. But the propensity is, like, it will clearly say that yes, this guy will show interest in taking the loan, yes, this guy will show interest in taking the travel card or something like that. Clear? In terms of business I'm talking about. Clear? Yeah, please. Generative AI. Okay. uh, I have that concept in natural language processing. Can I cover that there? Okay, cool. With that, I will let Bhartendu take over this. He will walk you through some of the computer vision concepts. Sorry, I have taken a lot of your time, but we have to rush. BK, please go ahead.
Okay. Thanks, Ashok. So, can anyone confirm if I'm audible till the end of wherever students are sitting?
Just ask him to increase volume. Yeah. You guys are able to hear him, right? Yeah, BK. Loud and clear? Yeah.
Okay,
What's
so
his name?
Ashok, like, help me take some questions whenever I ask or they ask. Okay.
Definitely.
Okay. So, can we move over to the slide?
Just ask to BK to increase volume.
Okay. BK, one quick question. Are you in full volume? Because there is some disturbance as well, I guess, if I'm not wrong.
From my end, I'm in clear silent room. So
Okay, awesome. I'll let the folks take care of this volume part. Can you check with him? Is there a possible to increase the volume, or that's the maximum we have? BK, I guess that's the maximum we have. Maybe you can just go ahead, and if there are any questions, I'll let you know. We'll see.
Okay, great.
Yeah.
Okay, so once again, hi everyone. As I already introduced, I'm working as an ML scientist here at PayPal, and we are working and dealing with forecasting, recommendation, all those propensities problem here at PayPal as well. But at the same time, there is a vast area of computer vision, which I got a chance to explore in my previous companies, as well as there are some use cases here also. So I want to discuss about that part of deep learning. So deep learning, we have a lot of applications, right? But vast amount of application come in that computer vision domain only. So Ashok, can we move to the slide, please? Slide number 9.
Yeah. Should I move to the next slide?
No, this one. Okay, it was.
Should I maximize it? How about now? begin?
I can just see a very small portion at my end.
Oh,
Yes, this is better. Just go to slide number 9, please.
slide number 9, right?
Yes, next one.
Yeah.
Okay. So computer vision is not something new. It is has been there from at least around 80 to 90 years, and even past few decades there has been a lot of computer vision application in industries, like sorting of the seeds, crops, and even fruits. And they were even able to run it vastly real time, right? But what was the problem in all those application was they were very much dedicated. It takes a person to research over multiple years to come up with such particular designs just to sort a particular red apple from a green apple, right? And then based on how much fps they can support with that time of camera and their hardware, these applications has been running. Computer vision is not new, but deep learning and computer vision coming together is something which happened like 10 years back only in this decade. So there used to be a lot of folks who used to actually spend like their entire PhDs coming up with such handcrafted features, right? And they used to come up with a very complicated algorithms which can do a lot of variations. So these are some conventional problems which computer vision was having, and some of them are those handcrafted feature limited to the robustness, like if the lighting condition change, you need to update your algorithm. Lack of generalization, if you built an algorithm to sort the good apple versus bad apple, you are scaling it to some other fruit similar to apple, but still you would have to do a vast amount of changes in the algorithm. Then very high dependencies on the pre-processing, your algorithm response, the time it consumes, everything will change the way you pre-process. Higher dependency used to be there to find contours and edges, all those things. Then any complex task which requires multiple level of understanding, like recognize image and then tell its location. So all those were very complicated algorithm must be built, and people actually used to spend years and years coming up with such algorithms. So can we go to the next slide, Ashok?
Yeah, sure.
Yeah. So once we had the deep learning at our disposal, we saw that these tasks became very convenient, because just imagine image as a 2D matrix, and you want to apply a filter operation, a blur operation. You want to just map it to something, which classification is nothing but you are taking in an image and you are mapping it to a couple of outputs you have with the maximal probability it should be mapped correctly. That is all about classification, right? So basically, you take a big chunk of matrices and apply a lot of filters through different layers, and it was able to solve almost any objective given. It was able to give regression value, like you can ask how much amount of rain is there. It can tell you weather condition, road types. It works wonder, and just coming up with that CNN architectures, right? So I'll go into that, and I have designed these slides for you. So basics I would have to skip because I'll not go explaining right now the filters and the strides and tooling. But feel free to reach out anytime, and my colleague is there. You can ask him all these questions as well. So with deep learning, we had this advantages, like we can conduct end-to-end learning with a single shot. We can have our extraction, selection, classification, localization, all those things with a single shot of training. Can handle a large scale of data in terms of all the variations and everything we can train, and it will give us much more generalized model, right? So if you change certain brightness or a condition became a little darker, it doesn't going to matter that much for a deep learning algorithm, because it has learned multiple layers of iterations and learning it had, right? And it could beat almost a lot of problem you would have seen in past 5 years, that it has been compared against human intelligence also, and it has been able to beat high professionals also into detection, real-time detection, etc. And plus, a human can process probably 5 images in a second. With deep learning and a good set of hardware, you can go any millions of images in a second also, which is happening with all this mass social media platforms where like instantly millions of images are being uploaded, removed, transferred, shared, right? So these things are analyzed in very fast capabilities now. There are also concepts of image compression, like you are having an HD video here, and when you dial a video call to your family, it's not actually sending all that high dimension images there. It just compresses right there in your phone or over the network and send that compressed format, and then it comes back into the resolution which you are sending from here. So such level of optimizations are going on. Same does the Netflix. Like you probably see multiple platforms giving you different streaming experience. So that is also happening with who has that level of compression available at their disposal. And then comes like transfer learning and pre-trained models. So if suppose you are trying to do something very particular where you don't have much of a data, like if you are at IIT, you will see a lot of research going around which will be like very niche. They would be trying to detect or classify something which probably they have only 50 images or 100 or few only. So in that sort of scenarios, they can pick an existing model which has learned how to extract those features and what to be learned from such similar images. And just with the transfer learning, and there are other Bayesian methods which can support very minimal set of data set also can help you achieve a task, right? So that also gives us that flexibility and adaptability of the learning models. So you move to next slide, Ashok.
Yeah, sure.
Okay, so here there is a simple problem mentioned. We have a plant seedling on a dirt basically, and with we have both tools available. We have computer vision tool, we have deep learning tool. So in the audience, please ask Ashok, like if someone want to try the problem, like how would they approach it with the image processing and how would they approach it with deep learning? Does anyone want to give a try, Ashok?
Yeah, any questions? I mean, any tries on what he asked? So BK, there was a question. So, like one of the students is asking to explain each one of this in brief.
Each one of the method in brief.
You mean the method? Yeah.
Okay, sure, I will give it a try. Okay, so first I will answer the problem itself, like how will we solve this. So here we have a color, right, which we can see is green, and we can see that it is able to form some ellipse shape as well, right? So probably attacking the problem, like if we can extract that color at the same time, if we can morph those shapes, those things can help us generate that entire mask that portion out of the picture, right? So that is the conventional method. And deep learning method is like there are already available segmentations model, or if you can just do some manual masking for few image and then use a few short segmentation model that can help you generate mask for any n number of images you will provide. And how to identify the plant seedling using both of these methods. So with conventional method, what you will do, you will have a lookup of multiple types of seedlings, and you will have them in different view. You will have the ratios that if they are fine, their leaf looks like an ellipse, what is the ratio? If their leaf look like a circle, how much the aspect to the stem should be there. Such methods are there to identify this. But with deep learning, we can just have a labeled data set of such images, do some episodes and epochs of training, and that would be enough to classify it in number of times, right? So I'll quickly try to explain the method as per request. So color maps, we have multiple color maps like RGB, HSV. So these are different representation of the same pixel, which help us perceive different view of from that image. One way I'll tell you that if you use separation values, they help us dig deeper into brightness, etc. And there are other channels are there which help us understand how much is the white component in that. So suppose if you are trying to detect how much ice is there or if the weather is snowy, in such cases you can just use color max, it will be able to help you. Image enhancements are basically like sharpening, denoising, those things. Edge and contour detection. So edges can be like all the edges present in a chair or a table, like even very sharp noises can also become an edge. And contour is the overall hull shape of that particular object. That is called contour detection. Image filtering is a technique where you can actually apply some filters, which is the major part of convolutional network also to learn that filters. But earlier to that, we used to manually design some filters which help us either detect an edge, blur the image, or some particular task if we want to preserve one particular color channel, etc. Thresholding and segmentations are basically like if you have an image and there is like even this image, right? If I can come up with a particular Otsu threshold or even a binary threshold, it can help me like almost get the same lookup of this plant seedling, right? And then a structural understanding, like considering the object as a, like you can estimate that it can, the leaf is looking like ellipse. So not one ellipse, but multiple ellipses are there. Each leaf can be morphed into an understanding in such a structural way. So that is structural understanding. Shift and on features are those gradients which gives us information in terms of image similarity and if we want to do object tracking, etc. So if you have a video and the sequence of pixels are moving in certain directions, right? This helps us understand that. Like this features can even go deep into, like if you want to just see a scratch on a car, right? These sort of features can help you understand if there were such scratches, lines on those car or any object. So in deep learning also, I'll explain these concepts quickly. So cost function is basically that loss function which will try let learn that particular network and update its weights, right? So a network will have layers. Each layer have filters. So filters are basically the weights. So earlier, my friend has already explained you the single neuron. So in that single neuron, you have the weight and the activation as well as the bias, right? So here in convolution neural network, that becomes the filter. So that is what we are trying to learn. Activation functions help you understand non-linearity and help you map the complex problem to direct to some particular input, right? Because if you don't have activation, you will keep on passing the same input multiplied with some certain weights, whether being positive or negative. So to have that non-linearity and infuse the learning into a deeper level, you need those activations. And the cost function is the reason why all these weights change in the first place, and it makes the network to learn those particular portion which will help it minimize the cost function. Optimization methods are basically what relevant algorithm which you will choose to have a faster training basically. So once you have these gradient values, right, once you do that weight update, choosing an optimizer help you that how fastly you want to change the those weights and how efficiently you want to do it. MLP is just connection of these neurons, and a multiple layer of MLP will be considered as density. Convolutional neural network, you don't have these fully connections of neuron, rather you have filters for which you learn weights. The convolution layer can be in multiple dimension. 1D convolution layer can help you understand horizontal variance, vertical variance, etc. Of course, non-image problem if you have, then also 1D scan can be helpful and give you some results like tree-based methods, right? Cooling layers just help you compress the the image in starting itself, as well as whatever feature outcomes are there, they also might be at a higher shape and size. The cooling layer just help you compress that or like make it resize to a smaller dimension by using max, mean, median, multiple sort of values and methods. Then there are other layers in the CNN which can help you add two features or take a dot product or concatenate them, etc. RNN and LSTM layers help you preserve some information, especially in terms of sequence to sequence modeling and the text and NLP problems which Ashok will be taking forward. And then we have the transfer learning and feature extraction, which I discussed in previous slide. So I tried covering all the tools which are mentioned here. It was not my prime objective, but I'll keep it going. And if any further questions are there, please reach out to me as well as my colleague is there. You can ask him as well. Ashok, can we go to next slide?
Sure.
Okay. So I have divided this entire computer vision problem in three parts. First one is the basic learning objective. Next one you will be seeing will be little bit advanced learning objectives, and final will be the generative learning. Right. So in basic learning objectives we have a regression. So an example will be you are getting an image or a frame from a live video, and you want to predict how much steering of the car you need to rotate. That can be a positive angle as well as negative angle, right? So that is a regression problem for that image. So looking at the image, you are trying to predict how much to spare, right? Then image classification. A lot of example are already there, so I'll skip that. A simple example can be the seedling. Other in a previous picture we saw, right? So different plants have different type of seedlings. That's actually a complicated problem also to identify a plant in such a small stage, right? So such problems are image classification problems. Image similarity problem is basically helps us do facial recognition, handwriting recognition, signature recognition, all these things. So what happened? There are two parallel networks called sister networks which share the same weight, and when two images are passed through that, we get two types of encoding or expected features. What we do, we take a Euclidean distance calculation or triplet loss. We can use multiple losses there, but best is to use some distance metrics, which in most cases will be Euclidean, and then we get a particular distance. Like that can be a probably some real value like 98 or 95, right? And that distance we apply a sigmoid, and we get a similarity score, which is between 0 to 1. And then you can decide the cutoff, like if you are building a facial recognition application, right? You can decide that if my sigmoid output is greater than zero point 0.5, it is still not clear if it is the same person. So I'll probably choose zero point 0.8 or zero point 0.9. So such things are possible with deep learning. It has been also possible with the conventional this thing, computer vision also. But in that case, you need to design very sophisticated and complex algorithm. You need to pinpoint facial points. You need to construct contours on the face, right? But here you see, like compared to that, it's become how much simpler. You have two networks which are basically the same. They extract features for from two images. One is the comparative image, and one is the real image which is coming. And you just get a similarity score. That's it in the while, right? Then there are multiple multi-level problems. Like suppose if you are like everyone is having a wearing a t-shirt or a shirt, right? So if suppose we want to fully recognize that what apparel you are wearing, so that apparel can have multiple types. It can be summer collection, winter collection. It can be a t-shirt, shirt, pant, right? So that problem is just I want to recognize what is the apparel, but that apparel can be into multiple category. It can be of multiple collection. It can be of multiple color. So how would you be able to recognize someone wearing a blue shirt, full sleeves, and so shirt is a recognition, full sleeve being a recognition, blue color is a recognition, and that someone being a male, that is the fourth this thing recognition, right? So basically, we are trying to classify multiple things, basically multiple labels, each label having their own class. So such problem will be called multi-label problems. So you like color, you can have 12 set of colors. Clothing apparel, you will have four types, and then gender, you will have male, female, boy, and girl. So four types of gender. So such problem becomes multi-level problem because each label is again multi-class. So that is called multi-level problem. Now coming to multitask model. So multi-label and multitask are like even you will see a lot of beginner level data scientists will be very much confused within these things. So I would try to explain. Multitask models help you do two different tasks itself. So how would you do it? Like you will create a single layer, and then you will branch it out to two multiple fully connected networks that can be also in a network, which do two different things. So let's take the example of sticky angle prediction. Or plant growth monitoring. So if we want to understand what type of plant it is, so that is a classification task. And then we want to say that it is growing well, right? So that growth can be basically if the leaves are looking good, if the internodal stem distance is good. So all those things are factor for growth. But what type of plant it is, like those features will be understood through the plant leaves and color of the plant and all. So just imagine different color leaves or different shape of leaf can all be in good health or a bad health, right? And different plant will have different characteristic of leaf and stem. So they are two different tasks we are trying to achieve with the same model, because at the end you can do those tasks and because your base image is same. So you can design such networks which will have a base CNN network. It will extract low-level features, and then you can connect it with multiple fully connected networks with multiple objectives. An objective can be classification with cross entropy loss. Another can be regression with mean square error and other losses, right? So you are trying to achieve two different tasks. Those models are called multitask models. So I'll pause for one or two questions only. Ashok, could you help me get the questions?
Any questions so far on this multitasking and supervised learning, or any questions? BK, I guess we have 0 questions. Maybe you can continue.
Okay.
You want me to
Okay.
go to the next slide? BK?
Yes, yes. Can we move to next one?
Yeah.
So here, guys, like I have picked the example of this steering angle prediction also, and I have explained here in detail. So how do we attack this problem in industry? So first thing, what we are trying to achieve here is like the images are coming in real time, and we want a model which in real time can give a response that this much steering angle should be there given that image, right? And we need to keep in mind that there are a lot of models available from ResNet to DarkNet, InceptionNet, and multiple versions of them. And we need to see what problem we are trying to achieve. And based on that, we need to choose those models. So suppose if your car is equipped with only very limited power GPUs and all, you probably cannot initiate multiple darknet tools, right? So I'll explain you how to Ashok, I'm getting my voice back. It's kind of hindering me every.
Sorry, BK, can you come again?
I'm able to hear myself back.
Oh, is it?
Is coming at my. It's increasing actually.
Let me put my mic away from the laptop and see. How about now?
Okay. It's little better. Yeah. Okay. So we have the steering prediction example here where we are having images in real time and we want an optimized network to help us achieve that. So one such network is PoliceNet, which has been a base of lot of residual networks as well, and coming forward lot of other network also associated with it. So what it does, like when the engineer want to design such network, what he thinks. So he came up with some design strategies, like rather than using 3+3 filters in start, I'll go ahead with 1x1 filters. I'll decrease it. You will see that people just writing a CNN and all, they'll put a random number like 64 filters or 256 filters without actually looking into deeper meaning that why I'm putting that much filter. Is it really required for the problem I'm doing, right? So such design strategies, once you are getting into this field and getting yourself experience, so ask yourself these things: that do I really need 100-layer network? Can I solve it with 10 layers? If I want to solve it with 10 layers, what type of filters or activation cell I pick? So those things are very important when you are attacking a problem. And a wide practice is just picking anything and retraining and adding a GitHub code. So that would make you a machine learning engineer. But if you really want to contribute in this field, right? In that case, you need to ask yourself more deeper questions, right? So such as the authors did, like they came up with just a very smart network, which was having 10x lesser parameters than current resolute models, and it was able to give exact same performance, right? So, when you are having an architecture and you are having a data set, you will conduct few data processings. So, in this case, you can see the data processing is like cropping out the sky, because that sky is an irrelevant portion for making the steering angle decision, right? So you optimize it better. So your camera is functioning at certain resolution, but probably 30% portion is not required to make a decision. So you write up the same 30% of computation. So and there are the augmentation techniques, right? Once you are having a data collection request, like once you are in industry, not all the data will be readily available to you. So you would make such request to get such data, and it adds cost to the company. So at that particular time, you have to come up with smart ways to utilize minimum set of data and come up with the best performance. So in this case, like if suppose you are unable to get all day to night images, in what you can do is you can play around with the thresholds to change the brightness and change a lot of aspect of the image and augment it. You can slightly distort it and still let your network make better predictions of it. So originally, this particular image you can see, right? That was a video which I have done as a POC when I was a student like you. So I'm unable to play right now because it's a PDF, so we'll skip it. In this image, you see that there is a straight path, and then there is a steering angle in a current state. But in the next state, we need a steering angle to move right or left or stay at the same angle. So in that case, we want the deep learning to make the decision. And we were adding the attention mapping at that particular time, 6 to 7 years back, and we wanted to see what are those regions in those images which are helping which are contributing in the decision whether to take right, whether to take left. How these things are done is like you take input image and then you see from your network which are those most active gradients from the output end. And those gradients back propagate. Like even in the training, we do by back propagation, right? So some of we just see in that image what is the gradient value, and that gradient is reflecting to the input space where it is able to create the maximum impact. So that particular regions are mentioned like highlighted here in terms of a red. And if this video would have been playing, like you would have seen the moment lane is there, the right turn is there. So it was able to beautifully find out both heat map regions while making the steering angle decision. So that's all. So it is a regression problem, and suppose you are dealing with this problem, what type of loss function will you choose? So that is my question, Ashok. If you can take answers, what loss function would you choose for steering and your prediction, and why?
So any tries, what kind of loss function will be used? BK, you want to repeat the question? Maybe mean square? Mean square root? Mean squared error? Yeah, so one person said mean squared error, BK.
Okay, great.
Yeah,
So
it's like people want you to repeat the question. Maybe they want to think
yeah, the
through.
question is like steering angle prediction we want to do, and the steering angle will go from minus 90 degree to plus 90 degree. In that particular case, what is the best loss function to go ahead with? We have mean square error, mean absolute error, and mean square logarithmic error as well.
So I need mean squared error. People are saying mean squared error.
Okay, great. So in deep learning, one beauty is there that almost any given correct loss function you use, it will end up in the convergence in any way. So probably it might take some lesser time or more time, but well-defined loss function to that objective can drastically let you have a, a shoot in the performance, right? So in this particular case, if we take a logarithmic scale error, that might not help because we are not dealing a regression problem whose values are starting in very large or uh, and ending up on like some minus infinity to infinity scale. Our scale is limited. We are trying to predict an angle from minus 90 degree to positive 90 degree. And what we observed going with either mean square or mean absolute error was giving the same amount of learning, but mean absolute error was the one which won in this particular same network, same amount of training, same images. The absolute error was able to give better prediction. And that's why, like when we are designing a network, right, there is a straightaway loss function for for classification which are cross entropy loss, right? And then there is something binary focal cross entropy loss, which focus on harder example. And these type of texts are available in research. So once you are in the industry or in your academia, and once you are developing such network, try to look into all this research and try to think like if this loss is there, what kind of impact it will have on the learning, and try it out. So don't stick to the what commonly used loss functions are. Just try to explore more and add more value to the research, right? Okay. So I'll start speeding up also. I already took 30 minutes. Ashok, can you go to next slide?
Sure.
Okay, so now we discussed the basic objective, which were like regression, classifications, multi-label, and multitask. Now let's discuss some advanced objective like detections. So detection objectives, like I mentioned it as objective, but there are multiple problems. One is like object detection. So here that object detection would mean drawing basically a bounding box and able to what object that is. So for such algorithms, we use localization losses, which is able to help us map in which particular area of the input should the box come or should the object be present. And also there will be a parallel classification loss. So in whatever area predicted by that network, how like is the object complete, and if that object is there, is it able to be classified? So those sort of losses together helps object detection. Some of the design models are there, are RCNN, YOLO, and SSBs. They are widely used in autonomous driving to detect lanes, detect signals, detect objects, detect trees, and then robotics, right? Once robot becomes more advanced and start actually speaking and interacting with you, right? So you will be an object with robots, right? And there will be the robot also needs to localize itself and identify all the surroundings. In those places, object detection. Image segmentation. So segmentation is like if you see below, there are two images, right? One of them you can segment person and object as well as the landscape. Another image you can segment three different type of person also. One is a boy, a man, and a woman, right? So that particular segmentation is called instant segmentation, where you are able to segment each instant, and other one is called semantic segmentation, where you are able to segment the type of it. So humans being one type, so that is semantic. The sky is there in background, that is another semantic. So there is semantic segmentation as well as instant segmentation. Basically, what is do? It is able to create a mask out on that particular image where any object is possible, right? So that is called segmentation. The best sort of designs which are available and easy to understand, and you can actually pick up and learn from that would be segment unit. Unit is like it has like made wonders in cell understanding. So cell segmentation and all this unit network was designed for that. I would encourage, like, if you get time, read that paper. And what type of learning we require in segmentation? Again, we want some intersection over union, that how much area was actually the mask, how much we were able to predict, what is the pixel wise cross entropy. Like if you are telling this is a person, right? That pixel belong to the pixel of a person, so that becomes basically a pixel level class. So we can apply a pixel level cross entropy. So those sort of losses help us learn image segmentation problem. The example of image segmentation will be medical image editing, background subtraction, video editing. So all these things, video is a frame of images, right? So whatever we can do in image can also apply to videos, right? So it helps in this type of problems. Then comes pose estimation. So pose estimation, you would have already seen multiple videos. The I need not explain what, like just pose of an object or a human, basically human of interest. So that pose we want to detect. It can help us activity recognition, etc. This can this has been starting to use in military application, where suppose there is an hostile environment, and without sending a troop, you want to understand what is happening there. So with short sort of using IR cameras, and there are other imaging techniques. They bring up some input images, and on that, with post estimation, quickly we can tell what type of activities are being conducted. Right? It also helps in sport analytics. It will help in augmented reality and robotics. So, what type of learning we require? We use heat map loss here. So basically, if there is poses will have edges and joints. Joints being like your elbow, your knees, all this will be appearing as a joint. So that area near the joint will have a heat map. So that is called joint heat map. There, if we are able to look into actual heat map of the joint and the predicted, we can take up the heat map loss. Indirectly, we can also have mean square error loss from the joint coordinates. So you basically we need to learn all those points which are the joints. And if suppose there was an actual joint in right corner and detected in left corner, there will be a lot of error, right? So a mean square error will be a large value. If it is coinciding in the same portion of the grid, it will be a very less error. So that's how the post networks learn, and examples are also listed. Finally, 3D reconstruction is not fully a detection objective, but I wanted to mention is basically you would have seen that you take a single shot image and now it will be able to give you a 3D reconstruction of it. So you take a picture of yourself and like there are technologies which can help estimate a 3D avatar of you. On that avatar, you can customization that could help build some sort of experience. Like say, if you are looking into a clothing industry and they want to recommend you some apparel. In that case, what they want to do, you take a picture, your avatar gets created, and you can choose and select and see in real time that how much that apparel suits you, etc. It can also work in any other buying experience that whether you are buying gadget, furniture, or even vehicles or cars, right? What other places 3D reconstructions are used are like computer graphics, of course, like all sort of futuristic movie we are seeing, right? So lot of those concepts are based on these 3D reconstruction techniques. Localization and movement for a robot, or if you are having a LiDAR and radar capacity. So even those drones also want to 3D reconstruct those environment to effectively navigate. So that sort of places 3D construction help, 3D reconstruction help, and we have augmented the reality and architectural use cases as well. So how do we learn 3D reconstruction? So we will basically be presented with 3D files, which we can send to a network is uh, which is capable of accepting a 3D input. 3D input just it will look like a matrix having L, B, and H. So it will be having what to say, three channels which will represent length, breadth, and the depth of it, right? So we can apply 3D CNNs on that, and one good example is 3D unit mesh CNN, and we use volumetric loss from earth mover distance. So these type of losses are able to compare the 3D reconstructed matrix value, the actual numerical value, to the existing numerical value. In that way, a network gets trained. And once the network is trained with enough good example, next time you get an image, the network is ready. The network is already capable of creating 3D avatar for you. So you can just take an image, it will pass through that network and it will be able to generate the 3D of you with a very minimal loss. So these are some detection objectives which are done using computer vision method, and the basis is basically deep learning. These types of techniques are very, very tough to do if you are going behind the conventional methods. And right now, entire research has shifted to the deep learning methods because we want more efficiency, we want better results, and we want it quick. So all three things are supported by deep learning. Finally, we have generative learning. So Ashok, next slide, please. So generative learning in this type of computer vision of deep learning program, our objective is to create a content, create a video, create an image, write a description, get an image out of it. So that all sort of creation objective can be supported by generative learning methods, right? So generative learning methods starts from variational autoencoders. Before that, we should know what is an autoencoder. So an autoencoder is nothing but if you have an X and you map it to X, and you learn a compression and you learn a decompression, like encoder and decoder. So that is basically called an autoencoder network. You give an input and you should be able to reconstruct the same output. That is the basic of autoencoder. And then you can even segmentation also you can refer as autoencoder networks, because in segmentation you are giving an output and you are reconstructing the same output with a mask, right? So all you are just dilating the pixels and making it a mask. So such networks are autoencoder networks where X is given and some X dash, which is a property of X only, is getting predicted, right? And the variational autoencoding, what it does, like when you are able to compress and the decompress, that particular area is called latent dimension. So in that latent dimension, a normal autoencoder just have some numerical value. They are entangled. You cannot tell what that numerical value means until you have the encoder. And if you add any values to those latent values, it will make a noisy image. You will get some image out of an autoencoder also, but that will be a noise because it does not have any genetic capability. So what does variational autoencoder does, that once you have encoded to decoder response, in the latent dimension, rather than learning those values, it approximates a distribution. And then there is a sampling operation. That sampling picks the sample from the
BK,
distribution.
should I go to the next slide because you're talking about variational autoencoders?
Come again, Ashok?
I mean, you're talking about the variational autoencoders, right? You want me to go to the next slide? Or
It's fine.
something?
I'll just browse through it because I think my 40 minutes is about to be done.
Okay,
Right?
okay.
Yeah. So in variational encoder, we try to learn that latent dimension. I'll speak more about it in the slide. And then GANs also is in the next slide. So let me talk about style transfer. So style transfer, what happens? You have a content image and you have a style image. You could be looking at probably a human only, and you are looking at Van Gogh painting. You want to translate that human to that Van Gogh style, right? So what happens that there is a base model, which will be a pretend CNN. It will give you the feature out of that content image, right? So that would be an input image, and that style image, which is like, let's say that the Van Gogh painting is there, right? So it will have a style features, and then the objective will be to generate an image. So in starting, the generated image will be basically your the content image only. You will repeat the same image at zero approx. But once it goes through the training, it will have a content loss, like content matching to the content, there will be a loss. And then content matching to a style, there will be a loss. This loss is very simple actually. This loss is just a reconstruction loss. It can be anything like mean square error or your mean absolute error. So that loss you look at from the content side to the generated image, as well as from generated image to the style. And you get two types of loss, content loss, style loss, and you try to optimize a weighted sum. So if you want it to be more like the painting, more like the style, then you will give more weightage to the style loss. If you want it to be look more original, you will give more weight to the content loss. So that's why if you are using some image editing app, right, they will give you a slider where you can just slide it out to have that much of what you say reconstruction or style transfer only. Like you can really move the slider, and far end of it will give you totally like the painting side of it, and the low end will give you the original image side of it. So that's how it is done. And the style transfer, you will use that loss. Then there are image captioning model, which are partially computer vision and partially this thing, natural language processing, which like Ashok will be talking about. So that models will deal with CNN in club with LSTM. So CNN networks help us understand the features of that image, and LSTM network learn from that caption, which is at the training phase present, right? And that image to text mapping is able to be created with the caption being in a caption encoded form and image being extracted feature form. And we can use simple loss functions like cross entropy also to achieve such tasks. These things help in creating summary of image. It helps in video summarization as well, and it also helps us getting content and knowledge. So suppose this can help us stop misinformation and all those news which are fake and they are spreading around, and in terms of images and all. So this sort of method can actually help to get content knowledge and block such items, right? So these are the applications. Style transfer application will be art, films, etc. And text to image, which is like diffusion model concept, you would have to like literally read through it. Will be, I cannot even explain it in 5 minutes. So that diffusion model used transformer concept and CNN concept, and it used image to text mapping. Basically, how it works is like image is there, features of image is there, we have mapping of the text. So from one side of the network, we are making it learn image to text, and another side of the network, same text we are using, and we are asking to regenerate the image, and we are giving such reconstruction loss, etc. And with those diffusion models, it is AI is actually capable of doing that. And in there, with this, like thanks to the hardware and the GPU accelerations which are available, otherwise this sort of model wouldn't have been possible for another few decades easily. But with such a high level of GPU and TPU machines we have right now, that this already incepted in this particular decade, right? So these are the models. Again, text to image models will be used in art, design, content, and concept. And you can just write a story, and in future, like within couple of years, people are trying it out already. You will write a short summary, and it will create a video for you out of that. So such capabilities are possible with text to image. In the next slide, there is some concept like yeah, of variational encoder and GAN. These are two main, like in the audience, whoever are intermediate knowledge with data science or machine learning, they'll easily follow this. So there are two known concepts of one is variational autoencoder, one is GAN. Both are able to create images, but both are having some slight distinction. And we are able to sample a value from the distribution. That's why it is called generative learning. If you do not have distribution learned or you are unable to sample, then it will be called noise. So the basic concept of generative learning, you should be able to approximate a distribution. So once it is able to approximate a distribution in variation autoencoder, we can explain those values, we can disentangle those values. So an example will be that if you trained a network from facial images to facial images, and next time you are generating a face, you can control these values, change the smile length, change the eye, change the face color. You will be actually seeing that how changing one particular written dimension or one particular number is changing this entire picture. So those are capability achieved by variational autoencoders. And if you want a very high resolution of images to be generated, and also those are we can generate with the help of GANs, right? So, GAN basically have a discriminator network and a generator network. Generator tries to generate a fake image, and there is a comparative real image, and then there is a discriminator, which have their own losses as well. Each have their own rewards as well. So if to explain a GAN, you would require a 30-minute separate session to do it, right? So in nutshell, there is a generator which try to generate an image, and then we have a real image or a discriminator and see the feature extracted from the real image and feature extracted to a fake image, and just do a comparison, and then gives a yes or no, like was it a correct image or not. And if correctly identified, that loss goes back to generator network, and generator try to optimize to basically build better and better fake images. So that fake image is nothing at the end of the day that become our generated image. So we use the generator, we give some noisy array, we give some certain value, and it is able to create high resolution, almost real images, because the training has happened in that. So all such network are able are our human creation only. We thought of using the same deep learning, shifting, like you see, all of the architectures are just like a length and width or an angled way of each other, right? So basically designing such network is important, able to make this network learn in the way a human can perceive, that is important. So focusing on all that, whenever you are looking at a research, focus on, is that network required? Could you contribute to the network? could you remove some network and make it more efficient? So that's what I would ask you to look forward. And I have put in the slide like those methods which are like bit easier to understand also, and plus it will give you a grasp of what the technology is already capable of, right? So after this session, please look deeper into it and feel free to reach out. I know I'm not physically present there and there's not much of an interaction, but you could drop a mail, message or anything and we can discuss it further. So with that said, I'll take final slide where I just want to let you know what are the career opportunities with the computer vision, right? So as we have machine learning researchers, AI engineers, and in general research scientists, those jobs are already there if you know end-to-end all the machine learning capacity. But if you want to focus on computer vision specific, these are few roles I have listed here for you. And what are the top places where you would be able to practice it like at the best level? So for computer vision engineer like Apple, Microsoft, and Amazon, you can focus. The job type will be optimizing a CV algorithm, coming up with a new CV algorithm and deep learning architecture, making integrate their OS devices so that nothing breaks down. That's why the optimization and efficient models become important. Then autonomous vehicle engineering. So you can look into Waymo, Tesla, Mercedes, Audi. So these are all trying to bring autonomous self-driving cars, which not only trying to bring, they have successfully brought. It's not there in India. We have level 2 of autonomy allowed in India so far. But in German countries, European countries, right, they are already running level 4 autonomous cars, which is basically you can just put a location A to B and just automatically go. So that if you want to contribute in that space, you should join as an autonomous vehicle engineer or just a computer vision engineer in these companies, which will be Waymo, Tesla, etc. The work will be perception, object detection, segmentation, localization, verification, all with the help of people. Then video analytics engineer, the big companies will be NVIDIA, Amazon recognition, Hacktivation, where you will be working on facial recognition, video surveillance, object tracking. Some military work also are there where they partner up and help them with devices and trackers, right? So such work is also there. Robotic engineering. So our AI is capable, but robotics still needs to follow. It will be a good space to work into, providing your computer vision knowledge there. The top companies will be Boston Dynamics, Tesla, SoftBank, Robotics, where the job will be perception, navigation, as well as decision making. So you'll be seeing bounding boxes, you'll be seeing the distance from the object or a person, you'll be seeing all the correct characteristics, but what is the best decision for that robot? So such task, a robotics engineer or robotics vision engineer would be a good position, right? And then the medical image analyst, GE Healthcare, Siemens will be the top companies. You can focus on medical image analysis, pathology, disease detection, and even plant and homeopathy, lot of application with those images you can do. So medical image analyst. Then AR, VR developer, all this 3D reconstruction or image or avatar reconstruction we discussed, right? So those are all coming to augmented and virtual reality. The top companies will be Magic Leap, Oculus, Facebook, and Microsoft. The jobs will be basically to come up with the app development of component developments for AR, VR, object tracking, and building experience for those users. So that is AR, VR developer roles. And finally, video game developers, right? So if you see, video games are also becoming more and more immersive. They are the way you play the video game also adapt to give you better challenge, right? So and you need to build its graphics, its component, mimic more of real world. So such positions are available in Electronic Art, Activision, Ubisoft. So these are some companies. If you are interested in a particular domain, you can target. So there, generative AI will come a lot of play in this video game development, where you need to create realistic graphics with immersive gameplay experience. So that's all. I have just listed the top ones which I could think of, or which were like I know of in lot of circles, right? But the application of computer vision is really vast. I probably covered only 30 to 50% of what computer vision and deep learning can do. So give weightage to your own research and look at optimization and efficiency because that will play the major role. So with that, I'll stop and I'll hand it over to Ashok. I'll be available on this call so that at the end also, if there is any question, we can discuss. So thank you all.
Thanks, VK, for walking us through different concepts of computer vision. So for time being, I'll not take questions in between. Park your questions for end of the session. I'll definitely answer those. I'll stay here for some more time after the session. So I'll quickly go over and whatever the questions you have, please just note that down. I'll try my best to answer them. Sorry. Coming to natural language processing. So natural language processing, most of us know, like we deal with the text processing, something like sentiment analysis, text summarization, chatbots, chat GPTs, right? So we heard a lot about that. So when you write a Gmail, right, when you write something, immediately it will recommend something, isn't it? Have you come across that? Yeah, that's the part of natural language processing. So it consumes the historically written information of yours and it will recommend something. Depends upon the context you're going to create, right? Context that you have shown to it. So that's the natural language processing. So there was an evolution after a transformer architecture. So I'll talk a little bit about that as well, and I'm sure I'll not bore you guys. I know it is a very lengthy session for you, but I'll keep it very crisp and short. So this is the evolution of natural language processing. Before the deep learning era, we used to have bag of words, TF-IDF, RNN, and after deep learning, we have RNN, LSTMs, and we have sequence to sequence model, which is which accepts input as a text, and it will generate the text. So when I said these suggestions in Gmail, right? The key model behind that could be the seq to sequence. So seq to sequence can also be used for creating chatbots. When you ask something, it can understand the context and it will respond to you accordingly. Or it can even crack jokes, depends upon the data you have, like whatever the task will be, like it will be able to understand it. And the next one is attention. I'll talk more about that in coming slides. And we have transformers, like I mentioned. After transformers, we have an evolution in NLP. Right now, we are seeing that ChatGPT is one of the best example. Whatever you ask, it will give you. If I'm not wrong, most of you guys are using that in your assignments and exams also, I know. So, and finally, we have GPT, which is related to ChatGPT. So now first I'll go to bag of words. I'll not go too deep into the technical part. So the first thing that you need to understand here is when you are trying to pass data to the deep learning model, it's supposed to be in numbers because it can't understand the strings. You are from CSE background, right? So you know what is the string is. So it can't understand apart from numerical information. So for that, we need to transform that into some numerical information, right? So initially, before the deep learning era, so we used to use bag of words. Bag of words are nothing but, tokenizing the words using the frequencies. As you can see here, we have a document, the cat sat. So the number of times the appeared in the document one is 1. So the will be represented with 1. At the same time, in the second document, the is repeated twice, so we have given the as 2. So here our ultimate goal is to convert the text into some numerical information. That is what we used to do previously, and that information will be passed to the model to perform our downstream tasks, right? But now, what is the issue with this? Quickly, any question, any answers on that? With this, what is the problem? Any one person, please. I don't want to take multiple questions. Yeah. Sorry, no. No, please. Exactly. Yeah. Exactly. So basically, the thing that is missing over here is context. For example, let's say I have a king, a word called king, and I have a word called boy. So is there any similarity between king and boy? We have, right? Because king is a boy, right? Let's say, so that is the context here. So you can't represent a king as a different word and boy as a different word, right? Because there is a relation. That relation we are missing. There is some similarity within the words which we are failing to capture over here because there is no proper contextual information. Let's say you know this Twitter sentiment analysis, right? I'll just quickly give you this example. So assume that you have built a model to restrict the curse words, right? Now, or also you want to build a model to find out the sarcasm. How the model will be able to understand the sarcasm if the model is not able to understand the context of it? It can't, right? It may think that they are actually giving the information, but in reality, the person who actually gives that information is very sarcastic, right? So such kind of contextual information is what we are missing over here, because of which the NLP was still, wasn't evolved at that particular time. So now after this, we have another concept which is TF-IDF, which is a term frequency and inverse document frequency, which is an extension of bagger words. But even here also, we are not capturing the contextual information. Why? Because if you look at the formula over there, TF and IDF, again, I'm not going to the math, I'm just highlighting what we have over here. It is taking the frequency of term as an input. So when you are taking the frequency of term as an input, ultimately you are adding some noise inside that. So even in the bag of words, we are taking the count of the word as our representations. So the representations that we are giving for a text is not meaningful, right? Because we are not actually creating anything meaningful. And if we are not creating anything meaningful, how come the model learns, right? So we need something that can learn the context of it, isn't it? So that is where we have word2vec. When during the initial stages of deep learning, when the deep learning was evolving, we have this concept of word2vec, which actually trains a model to understand the similarity. So now how we will understand the similarity? There are two concepts. One is continuous bag of words, and then one is skipgram. So when you have a list of words or a sentence, or let's say you have a line, right? Let's say in that line 4 or 5 different words you have. Now what we will do, we will randomly pick one word and we will make it as a target. With the help of other 4 words, we will try to predict that word. Let's say it's a kind of fill in the blanks, in our childhood, we have this fill in the blanks, right? We will be having access to the entire line, but some word will be missing. How we are able to predict that? How we are able to fill it? Any suggestions on that? How we are feeling that? Because we know the context of it, the before and afterwards we are able to understand, and based on that we are filling the blank, isn't it? Similarly, even the CBOW also does the same. So it tries to understand the before information and after information, and it predicts the word which is missing. Similarly, skipgram is inverse of CBOW. Like instead of taking all other words, it will only take a single word and predicts the rest of the words, which is a little complex, but ultimately we end up creating something meaningful. So we capture the context. So this particular word-to-vec model will give us some kind of a vector for each and every word. When you compare, let's assume that I'll give an example to make you better to make you understand. Let's say Ramayana, right? Like 1 second, sorry. Yeah, Ramayana, right? So when you feed that Ramayana to this particular model, and each and every word that occurred in Ramayana will have a vector, some numerical representation. So if I give Lord Rama and Raghunatha and also Hanuma, then the similarity between Lord Rama and Raghunatha will be higher because both are same, and the similarity between Rama and Hanuma will be very less because both are different persons. So the thing that you need to understand over here is like it is able to understand the context. When you say Lord Rama and Lord Raghunatha, the context is representing the same person. So it is able to understand that. So when you feed a huge corpus of Ramayana story to the model, it will be able to understand who is Lord Rama, who is Raghunatha, who is Hanuman. So the ultimate intention over here is to find out that context, which helps us to build a model which can create a very big impact in our downstream tasks like classification or sentiment analysis or generative AI, somebody asked, generative AI, so it plays a major role over there. And we have few other common methods also, doc to vec, fast text. I'm just going through, I'm not going to each and every point because of the time. So we have fast text, BERT and transformers. So we do have some other methods also compared to word to vec. These methods will perform even well, but word to vec is a very common method that everybody uses these days also. And these are some of the concepts we have to create that embeddings. Now, coming to the transformers, so this is what actually changed the whole picture of natural language processing or natural language understanding. So this is the architecture was proposed by Google in the research paper. Attention is all you need in the year 2017. So because of this, the current ChatGPT is running. The underlying concept of ChatGPT is transformers, right? So you might be asking, what is so different in this? If you ask me, this is nothing but a combination of multiple neural networks. That's it. Nothing different than that. But the only thing that is different is this attention mechanism. So attention mechanism is a kind of concept which changed the dimensions of the NLP. I'll talk about that in a while. But before that, we will see what exactly this transformer architecture is. So we have two different major modules over here, encoder and decoder. People who are in this domain might know about this encoder and decoders. So this encoder consumes, assume that you are building a chatbot. Let's say when you ask a question, hey, how you are doing? That's supposed to give, I'm fine, how about you, right? That's the use case for us right now. And we need to use this particular transformers to build that model. So now what encoders do, encoders accepts the question you ask, right? And it tries to understand the context using attention layers and the feed forward network. So feed forward network is nothing but the neural nets which I have explained in the initial sessions. We have discussed about this neurons and everything, right? So feed forward is nothing but the neural network. Attention mechanism is the only different thing that we could see over here in this particular architecture, and remaining else, everything is a deep neural network. So you don't have to worry about anything. Just try to understand what is attention and how that is playing a role in transformers. So like I mentioned, encoders accepts the text and it generates some information, and that information will be passed to the decoders. The second block is decoder. So the role of decoder, it understand what encoder learned, and it also understands what output we are passing, and it generate the text, right? So it accepts the text and generates the text. So when you ask, hey, how you are doing, then this decoder is the person who actually generates the text as a response. It responds like, I'm doing great, how about you, right? So this is how this transformers works. Like, I'm just giving a very brief information because of time, but the concept behind transformers is attention and the encoder and decoder. Now we will see what is this encoder and attention mechanism is. So this is the architecture of attention mechanism. So where we have Q, K, and V. Q is the query. When you have a question, when you ask a bot, then Q is the query. K is the key values that are available in our data. V is the learned vector, which will be the response of us. So that Q key values will be used and it will be passed to these layers. We have matmul and a scale function and also a softmax function at the top, which generates a probability, and at the end we are concatenating softmax output with V. Ultimately, this particular scale dot product addition is nothing but this particular formula, which is softmax of Q K T by root of D into V. So we are converting this particular formula to a neural network. That's it. Just remember that this particular formula is what attention is all about. And there is something else called multi-headed attention. So it's a kind of adding more attentions and taking the final value by taking a mean out of it. You know about this, right? When you have many numbers and you want to come up with a single number, you will take a mean out of it, isn't it? Average. So same thing happens here. So you have different strong models, different strong attention layers. Each attention layer will give you one output, and you will take the mean out of it at the end. That is what this second formula is talking about. So it's a concatenation of head 1 to head h. Let's say if your h value is 8, it takes output from each and every head and it concatenates, and finally the output will be shared to the feed forward network. Clear so far? I mean, what exactly this attention is all about? And also I'll tell you theoretically how this attention works. And also I will give some visual representations as well. Let me go to that so that you guys can understand well. So now look at the example one. We have the statement. The animal didn't cross the street because it was too tired, right? Now, when you apply attention, it tries to understand the relation between animal and it, and street and it. Any thoughts why we have a higher weightage for animal? Any thoughts? Sorry? Exactly. So attention is doing that. So what it does, it assigns certain weightages and it finds the relevant element which is very much relevant to the task you are doing, right? So here, it is representing animal, not street, isn't it? To conclude that, what we need to know, the context, the underlying information about the text, right? If we are able to capture that, then the context will be captured. So that is what the attention is doing here. So it tries to understand what you're talking about. When you're talking sarcastically, it will be able to understand because of attention. If there is no attention, no context information, no sarcasm will be detected, nothing else. It's just a simple plain machine learning model which works on the frequencies. That's it. Clear. Coming to the second example. So the animal didn't cross the street because it was too wide. So what it is representing? It is representing a street. Why? Because in this scenario, we have wide at the end. So wide couldn't be an animal with the previous informations. Wide could be a street, not an animal. So that's why it has a higher weightage with respect to street compared to the animal. So you try to understand why this kind of learning is important, how this learning is actually affecting our deep learning models, right? So now, uh, animal in the first scenario, animal has a higher weightage. So the model will think that this is something related to the animal. So let's say you are creating a classification model between thing and an animal, then it will give a right classification saying that you're talking about an animal, not about a thing. And when you talk about the second example, it will clearly states that it's not an animal, it's a thing. So this is how this attention actually helps us, right? So like I said, I'm not actually covering entire thing right now because of the time. But if you want to understand more about this transformers, I'll highly recommend to go through this attention is all you need research paper, because this is the base of any model right now. So now with that, I'll go to the second model, which is BERT, which is built on transformers. Most of you guys might know about this if you are in this data science domain. So BERT is one of the language learning model. Just like Word2Vec, it will create the embeddings for downstream tasks. Based on what? In Word2Vec, we have CBOW, which is continuous bag of words and scriptgram. But here we have two different concepts called masked LM and next sentence prediction. I'll quickly talk about that by looking at the diagram itself. So when you have a text, you randomly mask some words, just like filling the blanks. But in Word2Vec, you will mask only one word, but here 50% of your words will be masked, and you will train the model to predict it. So the context will be captured. Now coming to the next sentence prediction. So here we will talk about the relevant, the similarity between a text one and text two. When you have a sentence, there will be some, two different contexts, right? So now this particular model tries to understand whether those two sentences are relevant or not. Relevant, similar to each other or not. Will there be any relation or not? For example, if you take, let's say, let me give an example. I have went to Walmart. I raided the bike. Is there any relation between first statement and second statement? No, because I went to Walmart and where this I raided the bike came from. There is no relevant context between these two, right? But now let me give you this example. I went to Walmart and I bought a watermelon. Is this relevant? Yes, because the context of one is dependent on the context of two. So that is how they understand the context of a sentence as well. So this next sentence prediction and masked LM together can create a certain embeddings which can create a meaningful representation of a huge text as well. And one of the important thing of attention is When you have a huge text, let's say when you, like when you create a chatbot, if you give a very small question, then it can understand. What if you give a very huge text, 2 sentences or 3 sentences? It is even difficult for a person to understand, right? Because he has to remember and think what you have asked and respond. So for model, what we do, we use this attention so that the attention will give certain weightage to each and every word, like I mentioned in the examples previously, and it will understand the context and will give us the information. Clear so far? Now, if you're interested, I will talk about this. This is a kind of a walkthrough of a code, but I'll quickly skip to the overall process. So what you do, let's assume that you have a classification task, right? Somebody, your manager asked you to create a classification model. Now what you do? If you use bag of words or TF-IDF, you will fail. You will fail to capture the context. So now what you do, you have to come up with a certain kind of method which actually contains some context, isn't it? So now let's say your manager said, why don't you use BERT, which is implementable in our environment. So why don't you go for BERT, right? So then how you will create it? Then, like I mentioned, BERT is not a kind of model. It's a kind of language learning model which generates some embeddings. When I say embeddings, a meaningful representations of a text, right? So now what you do, you will pass your text to the BERT, and BERT will generate a certain vector for each and every text you have passed, right? And that vector will be similar to the other vector if in case the text is relevant to the other text we have. I mean, these vectors will show some kind of similarity if there is a similarity within the text itself. So these vectors will be used for the next model as a kind of features, and you will come up with a classification task. Like you have seen in this diagram, the text will be passed to the distal BERT, which is the other version of BERT, by the way, and that information will be passed to the logistic regression. You might know about this logistic regression as well, which is a very, very, very basic model in machine learning. So when you pass that to the logistic regression, the intuition behind adding the logistic regression is because logistic regression is very, very linear in nature, right? It can do wonders on linear data, but if it is non-linear data, then it can't work. It will not be able to show any patterns. It can't detect anything. So now the intuition behind adding that logistic regression is because the amount of features you're passing is very much in linear. That is what the intuition behind that. So when you pass that features to the logistic regression, then it means even with the logistic regression you are able to get a good accuracy because we are representing the text in a meaningful manner. So in NLP, it's not all about the model you use. Let's say you come up with some fancy model or some big architecture in neural network and you have come up with some 90% accuracy. In NLP especially, you have to represent the text in a such a way where the model can understand, right? And we have other version of BERT, which is Robota. I'll just skip this because I want to highlight things. And there is one more thing. This is the last slide I have, which is question and answering. You might have heard about this. When you go to a chatbot, when you ask a question, immediately it will give a relevant answer without any delay. How that is possible? So the chatbot will be created based on the logic of question and answering things. So when you ask a question, it will give an answer. And sometimes you won't be having a defined questions and answers. Sometimes what you have, you will be having a huge corpus like a book, right? And if somebody asks a question, you have to analyze it well so that it will give us a right answer. So how we do that? We use this particular architecture, which is from the Roberta. Let me give you an example. So let's say uh, today I have went to IIT Madras and took a session. Okay, let's say that today Ashok went to IIT Madras and took a session. Now, if somebody asks what Ashok did today, it said took a session in IIT Madras. How it will be able to say that? Because I have not even defined a question and answer kind of structure over there. I just given a statement and asked the model what Ashok is doing today. So it simply said that he has taken a session in IIT Madras. So what could be the reason? The reason is because here we train the model based on the extraction scenario. Like it extracts the information already present in the data. It is not summarizing anything. So you have the data. It will pick certain chunk of data which is required for your question. That's it. It will not do any kind of pre-processing also. It will look at your data itself. It will ask like it will respond to the question of yours only by looking at the huge chunk of data and see which part can be useful. It's a kind of extractive, not abstractive. So there are two types of summarizations. One is when you give a huge corpus and say, why don't you summarize it in a single line? You guys might have tried it in ChatGPT, right? So when you pass 100 lines of a text, and if you ask ChatGPT to write it in a single line, it will do that. That's an abstractive based summarization.